These are these are the topics that I'm going to be explaining today. I'm going to start off by explaining the coherence, volumes, and times of a neutron wave packet. Then I will focus a little bit on interference effects. Then I will explain coherence and incoherent scattering. And finally, I will focus on the sources of incoherent scattering. And then, of course, at the end, I will make a summary of the whole presentation. So if I'm not wrong, up until now, whenever we would explain a scattering event, we would always refer to the neutrons as plane waves or spherical waves. However, in a more general way, neutrons, in our case, but particles in general, can be described as a superposition of waves that travel as a unit with coherence. And these wave packets have several characteristics. As you can see in the slide, they're described with a Gaussian wave function. They have a central value of the kinetic energy, and they also value of the wave vector, central value of the wave vector. And they travel as a whole with a group velocity that is shown in the slide. But what I want you to focus on really is on the terms of coherence volume and coherence time that also define this wave packet. The coherence volume is a definite spatial. Sorry, the thing of Zoom is blocking my slide. So the coherence volume is the finite spatial size of the wave packet, and because it's a three-dimensional parameter, it can also be defined as the product of three different scattering lengths. Coherence lengths. And also remember that the neutron is traveling along the Z direction, and the vertical is Y, and the horizontal one is X. And also the coherence time. So as we have described this wave packet, it lives for a finite period of time, and this time is what is called the coherence time. So why are these two things so important? Well, when we have an experiment, we have several scattering nuclei, and we have an incoming neutron wave packet. So this neutron wave packet interacts with the sample, and the signal that we get will be a result of the scattering of that neutron wave packet with the nuclei within its coherence volume during its coherence time, giving rise to interference effects. So we have to keep that in mind. So what determines our coherence volumes and our coherence times in our neutron experiments? Well, for explaining that, we have to have a few formulas in mind that I show in this slide. And also we have to keep in mind that our uncertainties of position, momentum, energy, and time of our neutrons, they have to follow the Heisenberg uncertainty principle. So with that in mind, there are two stages that determine the volumes, the coherence volumes and times that we have in our neutron wave packet. The first stage is what I call the upstream, and the second stage is the downstream. So the upstream refers to the incident beam, what we do to have a good incident neutron for our experiment. So in our experiments, we do want that our initial state of the neutron is as well defined as possible. We want it to have a good well-defined momentum and a well-defined energy. And for that, I guess everyone's familiar with it. What we do is monochromate the beam and collimate it as well as we can. So that means that we are decreasing the uncertainty in momentum and in initial energy. So as a consequence, and because we have the rules of quantum mechanics present, the coherence volumes and coherence times of this neutron wave packet would increase. The same thing, something similar happens at the final stage of our experiment in the downstream when we detect our neutrons after they have interacted with our sample. We, of course, want to have the best resolution as possible when we do an experiment. So we want to know the exact momentum and exact energy after these neutrons have interacted with our sample. That means that the delta k of all three directions, so meaning that the uncertainties in or momentum and in energy, have to be as low as possible. And again, this as a consequences lead us to have a bigger coherence volume and coherence time. So basically, with this whole slide, what I'm trying to say, the point that I want to get across is that our coherence volumes and coherence time of our neutrons wave packet would increase as our resolution in the detection and in the collimation and the first incident state of our beam improve, which is what we want in our experiments. So this was quite general, but for the specific case of a diffraction experiment, we can explain a few little things. Well, first of all, the diffraction and diffraction experiment. In a diffraction experiment, we don't analyze the final energy. There's an absence of final energy, so we integrate over all of the energy exchanges that our neutron suffers after the interaction, right? Which is what is expressed with this formula. That means that our uncertainty in energy is maximal. So working a little bit with the formula, as I showed in the previous slide, we would get to a final coherence time that in this case of diffraction is called the snapshot time. And this snapshot time is much smaller than the actual movement, the characteristic time of the atomic motion. So what that means that when you perform a diffraction experiment, what you're doing is like taking a picture of your sample. The atoms of your sample are static when you perform a diffraction experiment. So that's why you have, it's like a static view, a snapshot, a picture of the atoms in your sample. In terms of spatial scales, because in diffraction usually we work with the Q vector. It's basically the same, but in terms of this Q vector. The coherence length is expressed as a function of this Q vector and probes the structure along its direction. However, I mentioned before that, well, this is just a summary of the slide. I mentioned before that in the as a result of this interaction with the sample, we would get interference effects, but I never really defined what it was. So this is very easy to explain with this experiment, the double slit experiment, that I guess most of us are familiar with it. So if we have an incoming neutron, a wave packet, a plane wave packet, and we have two slits, a wall with two slits, which size is smaller than the wavelength that describes this, we would get, well, they act as these characteristic centers, really. So we would get two spherical waves that interact with each other. And what does that mean? Well, that means that their effects summed, which is what this is what the principle of superposition is, really. And then here we have the detector, and we will get bright spots and dark spots. So the dark spots would mean that we have deconstructive interference, and the bright spots mean that we have constructive interference. So for the deconstructive interference, it means that the effects of both of the scattered spherical waves cancel out, while in the constructive interference, their effects summed up to get more energy or more amplitude in the signal. However, we cannot forget that our neutrons are actually particles as well as waves. So this is what I wanted to show you guys, this video, because I thought it was very cool how at the end we would get an interference pattern as well, like the one we had with the double slit experiment. Because actually when we perform experiments, what we're detecting are counts, or intensity are counts. So we see that we get the same kind of pattern here that we would get here, but in this first case, it's easy to visualize it as if it was waves. But these kind of effects, we get them as well with neutrons. However, we don't have slits when we're performing experiments like at the ILL for our thesis. What we have for atoms, right? And with this slide, I just wanted to show you that these scattering centers here are 2 atoms, but it's the same as the previous slides. We have an incoming plane wave that interacts with these 2 scattering centers that gave out an scattered spherical wave, and these 2 waves interact with each other, and we would get an interference pattern. Also, I would like to remind everyone that we would always have forward scattering, which corresponds to the transmitted beam. This is the last video that I'm going to show. I just wanted to show you guys a 3-dimensional animation so you guys could actually see and not in 2 dimensions. But the idea is the same. We have plane waves, and then we have a line of atoms, and then in the detector we'll get a pattern. However, I wanted to add and point out that the distances between all the atoms sorry, people are not seeing the video well. I hope the explanation was enough.
Yeah, it doesn't always work properly. We tested this earlier.
So many times.
It did work, but it doesn't always work properly.
Okay. Well, the explanation was enough, I hope.
Yeah, but you've also given the link, so they can enter the link by hand into a browser and see the video. Okay.
Okay, sorry. Well, anyway, this picture shows a little bit what I meant to say. That the line of atoms in this case, so the distances between the atoms have a result on the kind of pattern that we would get. So the point that I want to get across is that the symmetries and the distances between the atoms in the real world would affect the kind of pattern that we'll have at the end. And this is exactly what we do in experiments, right? We analyze the detected sorry, there's people talking in the chat. We analyze the detector, the signal that we detect, and to really know what we have in our samples, really. However, these 2 examples are not very realistic because you never have 2 atoms or a line of 9 atoms. This is not much more realistic because still there are 9 atoms. However, it's good to relate what we're actually used to see, which is a pattern like this, for some of us at least, with what is actually happened. I don't want to get into detail with this because also I think it's going to be the talk for the next seminar or in 2 weeks. But again, I want to point out that, for example, in this case in particular, we would have 3 families of planes, and each one of them has different interplanar distances. So each one of these family of planes would contribute to each of these peaks. And these are, again, a result of the interference effect that I was explaining before, but in a more practical way. However, we're not always working with perfect ordered samples or solids, or it can be very, very different. And I wanted to show you guys that, for example, if you are working, if you measure an amorphous sample, an amorphous solid, this signal would be like this. We wouldn't get sharp peaks or well-defined in the Q vector at all. However, although this is doesn't seem like you can analyze it, I guess in other kinds of experiments you can still get some information from these kind of data. And yes, well, I'm writing here that these amorphous, they don't have periodicity, and they're weak, they're correlated in a weak way. And yeah, so I will move on to the next block of my seminar, which has a lot of equations, to be honest, but I'll try to be clear. First of all, this is the starting point. So we're starting from the double diffraction cross-section that characterizes a general scattering process, neutron scattering process. And Pontus talked about this before. So I hope everyone has it fresh, but just a few reminders. Well, first of all, it's a general scattering process, and we're working within the monatomic case, so there are not any other element. We're working with like one element. And n is the number of nuclei of our samples, of the scattering centers of our samples, and J and J prime are the indexes that refer to each one of those scattering centers in the sample that we're studying. Again, Pontus said this before, we're using a Fermi pseudo-potential to describe the interaction between the neutron and the nuclei in our sample, and we're using the Born approximation. And also we see that the scattering lengths, which is B sub J and B sub J prime, they do play a big role in this double diffraction cross-section. And something that is very important, and for the next slides, it's important that we all have in mind, is that the values of these scattering lengths depend on the element, of course, but depend, because they were in a monatomic case, they are different depending on the isotope and the spin state. And well, we're also in the situation where there's no correlation between the scattering lengths and the atomic positions. So with that in mind, what we're going to do is play a little bit with this formula right here. So we're going to separate the first sum, this sum, into two terms. The first one, we're only considering the cases where J and J prime are different. And in the second sum, we would have those terms that we have ignored, which are the ones that J and J prime are the same. And after playing a little bit with it, we get to this expression right here. So again, here we have the terms of the sum in which J prime and J are different, and here the ones that J and J prime are the same. And the first term refers to what is called the distinct scattering. So it includes all like the scattering signal from the total scattering signal. This includes the signal corresponding to the interference from different atomic nuclei, atomic sites. And this would correspond to the ones that from self-interference from the same atomic nuclei. Well, this is a definition that is a little bit more theoretical, I'd say. This, of course, because cross sections are related to probabilities. Well, this expresses the probability of finding an atom at a position when another atom, another one, is at a specific place and time at the origin. While this one relates to the probability of finding an atom when that same atom was in the origin at time zero. Something that I want to point out is also that this is Q dependent, while this dependence in Q is lost when you actually develop the formula. You see that this doesn't depend on the angle. So this part of the signal will be isotropic. Well, this is just another way of expressing the same formula, but in a more compact way. So again, this big formula, we can still work a little bit more with it. And we get to the next step, which will be talking about coherent and incoherent scattering finally. So what we did here was including in the first term, again, the terms of the sum in which J and J prime can be the same. And because we're adding something in the expression, we need to remove it from the expression as well to respect the equality, of course. And so we get to these two big terms right here. The first term is the one that explains the coherent scattering, what we call coherent scattering, and the second term, the one that explains incoherent scattering. So what can we, from the formula, what can we say? Well, first of all, the first term, the coherent scattering one, is a function of the average of all the scattering lengths. And this is very important. And actually the coherence length is defined as the average, as the average of the of all the scattering lengths. Of course, maybe this is difficult to see if you haven't done all the math with the paper and pen, but this function, this coherent function, which is more compact here, has terms from distinct and self-scattering, while this other one, well, first of all, it doesn't, it's not a function of the average, it's a function of the variation from the average, which again will be very important in the future because I'll be talking about it. And the incoherence length is defined as the variance of the coherence length. The scattering length, sorry. And this term right here, it is only self-dependent. And for this reason, this part is isotropic, still not angle dependent, while this one it is. So after explaining this, I thought it was time to give an example that it was more visual, so these ideas could be more clear. So if we have a sample like this that imagine has two scattering lengths because we have several isotopes, two isotopes, randomly distributed and in a solid, in a solid sample, for example. Or signal, if we do perform an experiment, a diffraction experiment, would get a signal like this. But since what I mentioned before, is this total scattering signal can be separated into two different contributions. So we would get the coherent contribution from the scattering and the incoherent one. So I said before that the coherent one was a function of the average of all the scattering lengths, which is actually what is represented here, from an average of the whole the scattering lengths in our sample. This kind of signal arises. However, and this is Q dependent. However, the incoherent scattering is a result of the deviations of these scattering lengths. As you can see in black and red, the deviation from the average. And these deviations, what they do is contribute to this isotropic incoherent scattering. So I hope that with this, we clarified what this whole formula was a little bit more. However, this is what each of these terms mean, but what kind of information can we get from this coherent and incoherent scattering? Well, it really depends on the kind of experiment that we do. And I'm sure for every PhD project, each one of us specializes on different kind of experiments. So we study different things. But in general, because the coherent scattering comes from the distinct and the self part and is a scattering from the average, we usually are looking at collective phenomena. So for example, in this case, in diffraction experiments, we get information about, for example, the whole structure of our sample, or which is the Bragg peaks and the lattice structure. However, if we perform an elastic experiment, we would get an idea of the collective excitations, the phonons and magnons. Then the incoherent part, which again only comes from the self scattering part, again is a function of the variations of the scattering length. For the case of diffraction, I think it's more rare that you actually analyze this, but you still, I guess, you can study different parameters like magnetic form factors and measurements of the incoherent length. And in the case of inelastic scattering, I think it's more common. You can actually trace single atoms and study the atomic diffusion and things like this, which is what is represented in this little picture. So to finally finish with this block, I just wanted to show you guys this table where we have several scattering cross sections for different elements. And something that I want to point out, that I guess most of us are familiar with it, is that the incoherent part of the hydrogen element is much, much larger than the coherent part. So that means that, for example, if you are performing a diffraction experiment, like it's my case, would have a lot of background. And this is the reason why, for some experiments, you're advised to deuterate your samples, so you don't have that problem in some way. And also, something that I wanted to point out as well is that, for example, these elements right here, they have a very similar atomic number. However, the coherence scattering cross sections are very different, which wouldn't be the same with other kind of radiations that were neutrons. So what I want to say with this is that neutrons allow you to actually distinguish between these similar elements. So this is why neutrons are so useful in some cases. So to finish with this seminar, I wanted to talk a little bit about the sources of the incoherent scattering, which for me was the hardest part because it's not something that I really work with in my thesis. Again, this incoherent scattering has its source in the differences, the variance of the deviations I write here of the scattering lengths. Here I just write the theoretical expression. And because we said before that the scattering length depends on the isotope and the spin. So if we have a sample with the same element, and we have a distribution of isotopes of our spin states, we do have an incoherent contribution. So to explain this a little bit more, I separate this into 3 different cases of experiments that we could have. So all these ideas are a little bit more clear. So imagine for a moment that, well, always working with a monatomic sample, by the way. So imagine, for example, that you're working with a sample that has only one isotope, one spinless isotope. That means that the coherence, because we said that the coherence length, the scattering length, and is the average, right? So because there's like every scattering nuclei has the same scattering length, the average would be equal to the scattering length of that isotope. However, because we won't get any incoherent scattering, because I said before, it comes from the variance and the deviation from this average, but because all of the scattering lengths of our scattering centers are the same, we won't have that difference, that variance. So in this case, it would be 0. However, imagine right now that we have a sample with several isotopes. Well, and being C sub alpha the fraction of the isotope in the sample. Well, in this case, the coherence scattering length would be an actual average of all the scattering lengths that we have in our sample. So what we're doing here is basically averaging, and being this the fraction, so everything's well defined. However, because we do have a distribution of different isotopes, we do have some variations, and this is what is expressed here in this formula. I'm not sure if this is easy to follow if you haven't followed the whole procedure, but I hope it's clear, and if you have questions, you can always go back to it. But the thing is that if you have several isotopes, spinless isotopes, the incoherence scattering part would be a function of this incoherent scattering length. Things get a little bit more complicated when, instead of having a distribution of isotopes, you have different spin states, and we're working within the same isotope. So imagine we have a sample with only one isotope alpha and different spin states. In this case, we have to consider that our neutrons, the incident neutrons, have a spin, and the atoms of the sample have an angular momentum I. So both the pair neutron and nuclei would have a total spin J. So the things that these different spin states that this pair can have, they lead us to have different scattering lengths. Yes. With different abundance. So this for me was a little bit hard to understand actually, but we don't have much time to get into this. But yeah, so the different total spin that we have will have an effect on the scattering length and on its abundance. So when it comes to actually calculate the coherence length, well, you just have to do the average considering all these things. And for the incoherent part as well, you just have to do the variance to see the differences between the average of the coherent length and the and with the different scattering lengths that you have. And of course, you can also, I was actually thinking of put it in the slide. You can have a sample where you have different isotopes and different spin states, and it wouldn't be so difficult to actually develop a formula, but it would be a little bit big and messy. So I didn't want to add, but it would be the same idea. You consider the average, considering the different spin states and the different isotopes that you have, and then try to find a formula for the variance to get the incoherent contribution. So to sum up, just a little summary of all of the slides that I've shown today. I just want you guys to remember that the neutron coherence, regarding the neutron coherence and times, that is the incident neutron beam optics and the scattered neutron beam optics, they both determine the coherence volume and time of the scattering event. Then for constructive and deconstructive interference, well, this all depends on the superposition principle and at the detector, of course, so when all the waves have scattered from our sample. And then here I made a few notes about the case of diffraction and the case of elastic scattering, which Pontus mentioned before. And then for coherent and incoherent scattering, I guess from all the formulas, I just want you guys to remember that the coherent scattering length is basically the average. And this is why it gives rise to a signal that give us information about collective phenomena. However, the incoherent one, which is the variance of B, give us other kind of information. And again, I express this in terms of distinct or unself scattering. And the final thing that I mentioned before, it was the source of this incoherent scattering for the monatomic case, is that we have different isotopes and different nuclear spin states. These two things give rise to what we call the incoherent scattering. And this is basically it. These are the references that I used to prepare this presentation. And thanks to everyone for your attention, and thank you especially to the three scientists that helped us to do this seminar, and also to Palmerina, which she did this the same talk last year, and I used her slides for inspiration. And thank you to Pontus, because it was great working with him.